So now I briefly have just erased some parts of the board, and to answer this question, actually what to put here below and above the integration symbol, let's first consider an example for a curve. So again, we have our xy plane. And let's say a good example is the unit circle. And we would like to traverse the unit circle counterclockwise. This is already similar to what's stated here above, because here we also start at some point and we have some direction across we move along this path. Okay, it's a very bad circle. Sorry for this drawing, but I think everybody knows what is meant. And actually, but this unit circle can be described by, let's say, a vector xy and a parameter t. So let the x-axis be the cosine of t and the y component the sine of t. So when t equals 0, I start here because cosine of 0 is 0 and is 1 and sine of 0 is 0. And then I move here until t becomes pi half. And so forth. I move in this direction along the unit circle for increasing t. But then there is the notation that now x depends on t and y also depends on t. And then one says that the curve is parameterized with the parameter t. And in this case t would be an element of the real numbers. But one could also go into the negative direction. But generally one can then make a notation that dx over dt equals x prime of t, and dy over dt equals y prime of t. And one can write this a bit differently, namely dx equals x prime of t times dt, and dy equals y prime of t dt. And these two quantities can be inserted here. So I will not pause the video now. I think everything is stated here now when it comes to the example of the unit circle curve. So I will not erase this one, but everything that belongs to the unit circle. These two expressions here are important for further discussion. So the integral I will just copy from above over df equals the integral df over dx times x prime of t. I just plug in this dx here plus df over dy y prime of t and everything in brackets dt. But now I already know what to put here. It's just the t's that correspond to the starting and to the final point of the curve. let it be t1 and t2. So this is also called is also called a curve integral. But now with some property, namely by using the chain rule for two-dimensional functions, I just write it down here. The chain rule, let's say df over dt, let's say we have our function f and we parameterize x and t, then actually it's not partial derivatives. So then df over dt is equal to df over dx, dx over dt plus df over dy, dy over dt. But this is the same expression as here because x prime of t is dx over dt. Therefore, we can write here this integral with a different notation. So we have here df over dt being integrated between t1 and t2. And this is nothing but the function f itself evaluated at x of t2, y of t2 minus f dependent on x evaluated at t1 and y evaluated at t1. But this is a very important property, namely it means that this integral of the total differential does not depend on the path. It just depends on the values of the function itself evaluated at the beginning point and the ending point. But since this is now very important, I will explicitly write it down. So the exact differential is path independent. Sorry, I'm naive. Actually, and it is also defined by this property. Integrals over exact differentials are path independent. So now we already know what the exact or the total differential is. It is an expression for changes of a function, and if the integral over the total differential, the infinitesimally small change in the function value, when one integrates over this and this is path independent, then it is a total differential. Hopefully I got this correct. So to digest everything, let's make a summary board. So we have found expressions of the form that infinitesimally small change of some function x can be described by some, let's say, function p, which depends on x and y, plus q, which depends also on x and y dq. And if one has an expression of this form, then, and if it is indeed a total differential, meaning the p is the partial derivative of f with respect to x, and q is the partial derivative of f with respect to y, then, and all the preconditions we have stated in the beginning of this lecture apply, then we have an exact differential. This means that when we're integrating our curve, this integral solely depends on the difference between the function values at beginning and ending point of the curve. And if one moves across a closed path, then one denotes this here with a ring in the middle of the integral symbol, and actually I'll write it out. So it's the difference between the same function values, and this is 0. And one could do this for checking if one has, or if it's not a total differential, then one would have troubles finding the function f, or there is no function f. But a property to check for a total differential is that dp over dy equals dq over dx. So if this applies, then one deals with the total differential. To know where this expression comes from, I suggest looking up the curl of a vector field. So now the question remains, what is an inexact differential? It is solely that one can say that if one moves across a closed path, then the integral is generally not 0. So actually this is the end of this lecture about the total differential. Hope you liked the content. If yes, maybe give me a thumbs up, and hopefully we see each other during the next video.